the idea known as crystal field stabilization energy will help us determine which electron arrangement is more preferred. Crystal field stabilization energy, which is abbreviated CFSE, represents the stabilization of the d orbitals due to the presence of ligands. So the ligands stabilize the arrangement of d electrons on the metal cation. This decrease in energy of a coordinationist compound is caused by the splitting of the d orbitals. So the crystal field stabilization energy can be determined for coordination complexes using the following formula. The crystal field stabilization energy is equal to the number of the electrons in the T2G set times 2/5 of the crystal field stabilization energy for an octahedral complex minus the number of electrons in the EG set times 3/5 of the crystal field stabilization energy for an octahedral complex minus the pairing energy. Now, the contribution to the pairing energy is determined relative to the unsplit case. So let's take a look at an example. What I want to do now is to verify the expression for the crystal field stabilization energy for a T2G 5 electron configuration. That means all 5 electrons are in the T2G orbitals, and a T2G3 EG2 electron configuration. That means there's 3 electrons that are unpaired in the T2G orbitals and 2 electrons that are paired up, or that are unpaired, in the EG orbitals. So here's what we're looking at. For the T2G5 configuration, we're looking at this orbital diagram, or this crystal field splitting diagram. Notice that 4 of the electrons are paired up and 1 is unpaired, but all 5 of them are in the T2G orbitals. So we take the 5 electrons times 2/5 delta naught for the T2G set minus 0 times 3/5 delta naught for the EG set minus the number of pairs. So for the unsplit case, we should have 0 pairs of electrons. However, we have 2 pairs in the split case. So the crystal field stabilization energy for the low spin configuration is 10/5 times delta naught minus 2p. For the high spin case, notice that all of the electrons are unpaired. So it's going to be 3 times 2/5 delta naught for the T2G pair minus 2 times 3/5 delta naught for the EG pair minus 0, because there are 0 pairs of electrons. So the crystal field stabilization energy diagram, or stabilization energy expression, should be equal to 0. There's also a 5th component that affects the spin state of the coordination compound. We've talked about mainly the number of electrons on the transition metal cation, but the ligands also affect the spin state of the electrons on the transition metal cation. Okay. So the first 4 factors that we talked about that affect the spin state are all revolved around the nature of the metal cation. However, the ligands also affect the spin state of the electrons on the metal. So we're going to talk a little bit about that next. Factor number 5 is that the bulkiness of the ligand will affect the ability of the ligands to form bonds with the transition metal cation. The greater the bulk, the smaller the interaction between the ligand and the transition metal cation. And this leads to weaker interaction, so you get a high spin state. High spin, remember, is where you have less splitting of the d orbitals, and if your ligand isn't bonding very well to your metal cation, you're not going to get a tremendous amount of splitting of the d orbitals. So you should get a high spin state. So let's take a look now at the ability of ligands to split the metal d orbitals. There's actually an empirical or a list of how well ligands split the d orbitals. And this list is known as the spectrochemical series. The spectrochemical series is a series that orders the ligands in their ability to split the d orbitals. Some of it depends upon the bulkiness of the ligands. Some of it depends upon the nature of the ligands. How well do they interact with the metal cations? So ligands that interact very well with the metal cations split the field very well and always give low spin electron configurations of the d electrons on the metal cation. So CO and Cn-, they interact very, very strongly with the